In the orchards of South America, life unfolds in quiet layers, some visible and some impossibly small. Among the citrus groves and hanging fruit, countless creatures move through the branches, each with their own story. But some stories are so small, so subtle that they escape the human eye entirely. The South American fruit fly, Anastrepha fraterculus, is a tiny but notorious pest. It feeds on citrus and guava, drifting from tree to tree, shaping agriculture in ways farmers know all too well. To most, it is simply a speck with wings, a nuisance that spoils fruit and spreads through orchards with surprising persistence. But inside its cells, something far more mysterious resides, something that has been traveling with these flies for much longer than any human has been paying attention. Across many unrelated studies of these flies, researchers noticed a recurring whisper in the data. A small fragment of viral RNA that kept returning, no matter the location, the season, or the laboratory that sequenced it. Different projects, different years, different goals, yet with the same quiet signal appearing again and again, a virus that was hiding in plain sight. One dataset offered the clearest glimpse, a simple transcriptome of a fruit fly, not enriched for viruses, not part of any infection experiment, yet carrying a remarkably strong trace of this hidden agent. Nothing about the experiment should have revealed a virus, and yet the sequence shone through the background like a beacon, hinting that this organism was not a contaminant at all, but a long-term resident. The fragment turned out to be part of a viral RNA-dependent RNA polymerase, the enzyme used by RNA viruses to copy themselves. Even the small piece carried the ancient molecular fingerprint found across the viral world, a catalytic motif shared by everything from plant viruses to fungi viruses to those that infect animals. It was as if the virus had left behind its signature at the scene, quiet but unmistakable. Advanced structural prediction revealed a compact, elegant enzyme, loops and helices folded into a shape seen across plants, fungi, and insects, the mark of the Partitiviridae, a family of viruses known not for causing disease, but for coexisting quietly with their hosts, a viral lineage built not on aggression, but endurance. This virus appears again and again in fruit flies across the continent, in different regions, different habitats, different studies, each time with the same gentle presence. At times, it appears in related fly species, or faintly in samples from the surrounding environment. But nowhere does it bloom into outbreaks or devastation. Instead, it drifts with the flies themselves, passing through generations like an inherited whisper. Partitiviruses rarely cause symptoms. Instead, they settle into long-term relationships with their hosts, replicating just enough to survive, yet rarely enough to harm. In Anastrepha fraterculus, the small partitivirus behaves like a quiet passenger, persistent, stable, and almost certainly harmless. It does not shout for attention like some viral pathogens. It does not reshape ecosystems or cripple populations. Instead, it simply stays, a subtle part of the fly's molecular landscape. Hidden inside one of South America's most familiar insects, this virus, which we name Fraterculapartitivirus comitans, reveals a different kind of story, one of coexistence, subtlety, and the unseen biodiversity carried within every orchard. In the grand tapestry of life, not every virus seeks to conquer. Some choose a quieter path, some viruses shout, others simply stay.